In today's video, we'll be talking about energy. After watching this video, you should be able to know the difference between potential and kinetic energy, know the formulas for potential and kinetic energy, and gain a stronger understanding of energy conservation. So let's get right to it. The first type of energy I'd like to talk about is potential energy. And potential energy is just simply energy that's stored in an object that possesses energy to be able to do something, whether it be move or whatever the case may be. So it's not that it's in motion, it just has the potential to basically begin to go into motion. And the units of potential energy are the joule. Okay, so joules are the unit of potential energy. So there's something called gravitational potential energy. And gravitational potential energy is the energy stored in an object as a result of its vertical position or height. Okay, so the higher something is, the more potential energy it has. So kind of a simple example would be like if you're, well, I got to change pen colors here. If you're standing on the ground and here's the ground, and let's say you climb up into a tree. So now you're up here in this tree. You have much more gravitational potential up here in the tree than you do, say, when you're standing at the ground. Okay, so height is one piece to gravitational potential energy. The other piece to it is the amount of mass the object has. The more massive the object is, the more gravitational potential energy it gains per height. So as basically the variables state, the formula for gravitational potential energy is this: mass times the acceleration due to gravity, which typically is going to be 9.8 meters per second squared, times the height, or PE equals mgh. Okay, mass times gravity times height. Okay, so that's basically it. Okay, it's a relatively simple formula, but it kind of makes sense. If you're on the third floor of a building, you have much more gravitational potential energy than, say, if you're on the ground level of a building. All right, let's talk about elastic potential energy. This would be dealing with like springs, or another one would be like if you take a rubber band and you pull it apart. The rubber band, when it's taut, has energy stored in the material as a result of the stretching. Or in the case of like a spring, if you compress it too, it also would have energy stored in the spring itself. So the formula for elastic potential energy is 1/2 kx squared. Okay, and so there's some new variables here that I'll talk about. 1/2 is just 1/2, but K is something called the spring constant. And basically it's real simple. It's just how hard it is to stretch a spring. So a spring that has a high K will be very difficult to pull apart or compress, whereas a spring that has a low K value would be relatively easy to pull apart or compress. And we'll deal with this a little bit more, particularly in second semester. But for right now, just know that the spring constant is just how hard it is to stretch. And then X is the distance that you stretch it. Okay, so if you pull a spring apart, say a meter, that would be your distance. Okay, and that would be the X piece, and that is squared in this formula. Notice that it is squared. Okay, so that's called elastic potential energy. Kinetic energy. Kinetic is energy in motion or movement, okay, if you will. The formula for kinetic energy is Ke equals 1/2, so 1/2 mass times velocity squared. 1/2 mass times velocity squared. The more velocity you have, the more kinetic energy you have. So if you're going, 30 miles per hour down a road, you would have more kinetic energy than, say, someone who was just taking a walk down the road at, 4 miles per hour. Okay, energy or kinetic energy is a scalar. Okay, so you would not have to break this into components. You would not have to have a direction associated with it. It's just a scalar quantity, and again, the unit is the joule. Okay, so here would be the formula for kinetic energy. Mechanical energy is basically what we've been talking about. Any energy acquired by objects upon which work is done is mechanical energy. And so like I mentioned before, we had basically discussed the two types of mechanical energy, kinetic and potential. Okay, kinetic energy is motion. You're in movement. Potential energy is like stored energy. It has the ability to go into motion, but it hasn't been set off yet, if you will. An object that possesses mechanical energy is able to do work. And that's kind of the big overriding theme here is if you have energy, you have the ability to do work. So for example, if you put kinetic energy into a hammer to drive a nail into a board, that would be an example of energy doing work. Or you throw a bowling ball down an alley and you hit some pins at the end of the bowling alley, well, that would be kinetic energy being able to do work. Okay, so mechanical energy solely is just dealing with kinetic or potential energy, and all it is basically boils down to is that you have the ability to do work. The total mechanical energy of a system, which we have represented here TME, that's just an abbreviation for total mechanical energy, is basically the change in the total energy must equal the change in the kinetic energy plus the change in the potential energy. Okay, so like I'm going to do an example later on dealing with like a roller coaster, because roller coasters are a great example of kinetic and potential energy kind of changing as things go throughout. So keep that in mind. The total change in energy is the kinetic energy plus the potential energy plus this thing called Q. And Q basically is energy lost, and it's not that it's being destroyed, if you will, but basically it's lost to things that would be things like heat from friction, sound, light, and basically it all turns into heat is what ends up happening. And so that's just energy lost to kind of it doesn't serve a purpose in terms of doing work, if you will. It's just lost. So if you rub your hands together, that's kinetic energy, but some of that energy is being lost to the friction between your two hands, and you can feel that heat build up between your hands. Okay, and so this is basically an idea that is going to be overriding throughout the next couple lessons, where we're going to be talking about basically the conservation of energy and how it stays constant even though it just is changing forms. Okay, so as I mentioned in the previous slide, energy is not created, nor is it destroyed. Okay, it can't be created and it can't be destroyed. So all the energy we have in the universe, that's it. Okay, there's not being any more added. There's not being any that is lost. So the energy before equals the energy after. And the thing that's kind of hard to wrap your mind around, or at least can be, is that energy certainly can change forms. So it can go from kinetic energy to potential energy, back to kinetic energy, and it always can be lost to friction or sound or light or all those different types of cues that come into the equation. So what's kind of neat is that the kinetic energy before and the potential energy before must add up to the kinetic energy after and the potential energy after. And in some problems, we'll just say, it's a frictionless system. Okay, there's no friction. And so you don't even have to worry about Q because Q is 0. I mean, you certainly could put it in there. You could do plus 0 on either side, but that doesn't really change anything, right? So let's do a little look-see at a roller coaster. I'm just going to draw a picture here. Most roller coasters, they start off by taking you up to the top of a hill. I don't know if you've ever thought about, like, why is that? Well, basically, as you get up to the top of the hill, your potential energy is going way up, okay? You're getting more and more potential energy. And then they release you, and you go down a hill, okay? And what's happening is that potential energy, while it is decreasing, what is it being changed into? It's being changed into kinetic energy. And so you like ride down the hill, and then maybe you go up another little hill. So at this point here, right here, you would have, you'd be gaining potential energy, but you'd be slowing down, so you'd be losing kinetic energy. And it kind of is just this cycling pattern, I mean, in a roller coaster, you have an increase in potential energy, decrease in potential energy, an increase in kinetic energy, a decrease in kinetic energy. You just have to kind of think about what is the roller coaster doing. So there's actually a lot of physics going on in a roller coaster in terms of how energy is changing from one form to another. And through the whole thing, I'm kind of just making the assumption that the track is frictionless, even though that is not true. There certainly is energy being lost to friction. We're just kind of making this assumption that there is no friction. That takes care of this video. I will see you guys next time.